Welcome to this course on reinforcement learning. Reinforcement learning is a branch of machine learning. So let's first see what is machine learning and where reinforcement learning fits into it. So machine learning is categorized into three main categories: supervised learning, unsupervised learning, and reinforcement learning. Nowadays, semi-supervised learning term is also popular, but for the sake of simplicity, we will stick to these three main branches. In supervised learning, as the name suggests, there is some supervision or guidance present. So we provide a set of labeled data and also the corresponding output, and the job of the network is to learn using those well-labeled training data. And the main classes of supervised learning are classification and regression. So classification, as the name suggests, deals with categorizing the data into classes, whereas in regression we get some real valued output. So one example of classification would be that we are given some examples, sample images of cars and some images of bike or bicycle and some other vehicles, maybe bus. And we have labeled those objects in our images. So we provide the position where these are located in the image. So if we provide tons of data, like maybe 100K or 10K of such level data to our network, in this case for image processing, CNN, then ultimately the network will figure out what's the difference between the representation of a car to a bicycle or a bus. And ultimately, when we feed in new data to this trained neural network, it will be able to predict correctly whether the image belongs to the class of car, bike, or bus. So we can call the car as class 1 and bike as class 2 and class 3. So it will give out some discrete classes here, 3. Whereas in the case of regression, we may give some continuous data, like some housing prices are given, and we have given some input factors like number of bedrooms, area of the house, locality, and so on. So we have provided a bunch of such data and also the corresponding price of the house. So this will be some real number. So training our neural network with these sets of data will ultimately be able to predict the price of a new house. So when we feed in a set of bedrooms, house area, and the locality of the house, the network will be able to predict what should be the price of the house. So this will be example of a regression where it will predict some real valued output. In unsupervised learning, there is no supervisor or guidance. So here the network just tries to group the given data based on similarity, or tries to understand the hidden structure in the data and tries to find which data are similar and which data are different. And it will ultimately try to group similar data together. So the main classes of unsupervised learning are clustering and association. So clustering will mainly group different data points, whereas association would try to find some relation between different parameters. Like in the earlier class supervised learning example, we had 3 parameters, x1, x2, x3, and we were predicting y. And we had record 1 and output, second record, third record. So clustering would try to group and we had record 1 and output, second record, third record. So clustering would try to group these 2 records are similar, whereas association would try to find some association that this x3 is highly linked to x1. So whenever x1 is there, it's highly likely that X3 is also there. So these are related. So this is the difference between clustering and association, and these fall under the category of unsupervised learning. Finally, reinforcement learning, which is the main subject of this course. In reinforcement learning, there is no supervisor, but it has reward signals. And the main components of reinforcement learning are agent and environment. So agent takes some action based on some policy. So here by agent, I mean some algorithm. And it has some policy based on which it will take some action. And environment will emit certain observations depending on the action taken by the agent and also some reward. So data depends on the agent's action. For example, here there is no predefined set of data, and suppose we have a robot and it's trying to learn to walk. So if robot moves in this direction, it may get different types of observations, like some objects may be there in its way, and when it falls down it will receive negative reward from the environment and it will try to correct itself. Whereas if the robot would have moved in this direction, it would have observed different kind of experience and it would have uh, got some different observations. So here the data on which the agent is being trained depends on the action of the agent. Whereas in the case of supervised learning, we would have provided some fixed data set on which we will train our neural networks. So it's different from supervised learning. So some example of reinforcement learning could be learning to play chess, where the agent takes some step and it will get some positive or negative reward, and if it gets negative reward it will try to correct itself, and finally with lots of experience the agent will learn how to play chess. Similarly, flying helicopter could be one example of reinforcement learning, where the crashing helicopter we may give some negative reward, and for following some trajectory as we want, we would give some positive reward. And similarly, robot walk also comes under reinforcement learning. So thanks for watching, and don't forget to subscribe my channel for my future videos. So today I'm going to start a video series on reinforcement learning, and this is the first video in that series. So over the next few videos I will try to give a top view of reinforcement learning first. So this would be the first part of the introduction, and the main theme of this video would be agent and environment, because these are the major factors involved in reinforcement learning. So it's always a good idea to have a top view of what you are studying. So we can start looking at the main things in the next few lectures so that we get a overall picture, and then we will start exploring in depth those features. So straight away, if you start diving deep into one of those topics, you sometime lose the sight of where you are. So it's very important to first get a top view, then explore those things. So let's start. So first, most of you would be knowing that we classify the machine learning into major three categories, which fall under the bucket of supervised, unsupervised, and reinforcement learning. So supervised learning means that there is a supervisor. We have the input data as well as the output data. So for example, in image classification task, you may be given some, for training you will feed maybe 10,000 images of some class, maybe car, bike, and so on. So you label explicitly those 10,000 images with car and bike and where they are located in the image. So you have a labeled data. So there is kind of a supervision. You guide the neural network that at this part of the image there is a car located, and you try to figure out how you can represent a car by looking at a number of those examples. So classification would fall under supervised learning. Similarly, regression, like you have some data about maybe housing prices, and so you have various parameters like the number of rooms, the city in which the house is located, the area of the house, and many more factors, and also the price of the house and those things. So you feed the data and you also feed the output, that is the price of the house. So here we had discrete output, like if we have 5 classes, the output will be either 1, 2, 3, 4, or 5. But in the case of regression, we can have any continuous value. So these kind of things like regression and classification fall under the supervised learning problem. Whereas in unsupervised learning problem, you feed a bunch of data to the network, and it's the job of the network to figure out how some data are more related among themselves and some are less related. The best example would be the clustering example that we see often in when you open Google News. You will find that uh, some news like Facebook last year lost $120 billion in a single day of its market capitalization. So that was a kind of a record fall for any company in the history. So at that time, if you open Google News, you'd see one of those news, and also see that the same news is reported by different sources, and those would be clustered together. Like if click it, it will expand the various sources, and similarly some other news will be grouped in some other cluster. So this the network does in unsupervised fashion. It automatically finds out that these news items are very related, and it tries to group them together. So clustering would be example of unsupervised learning. Similarly, for reinforcement learning is a completely different paradigm here. The learning is governed by the notion of reward and reward, punishment, and these kind of approaches. And there is a concept of agent which takes the action based on some policy, and it interacts with environment, and environment gives out some observations and also some rewards to it based on its state and action. So we will mainly focus in this part of introductory video about how the agent and environment interact among themselves. So let's start with the reinforcement learning problem. So as I stated earlier, the agent and environment, these are the two main uh, concepts in the reinforcement learning. So agent takes some action. So this is this way. So agent affects the environment. So agent takes an action at time t, and in the next time step, agent receives a reward for its action corresponding to time t that it took in time t, time step t, and it also gets some observation. So remember these three flow of data. Agent takes some action, and in return it receives a reward and some new observation. And while comparing it with other machine learning paradigms, you see that in case of classification, you have predefined what are the 10,000 images on which you are going to train the neural network. So you have a fixed set of data, whereas in the reinforcement learning there is no such fixed data. Like if there is a robot and it's trying to do some operation by learning, then the next observation or the next reward it will receive will depend on its action. Like if robot starts from here and it goes in this direction, then there may be some obstacles in the path of this side, but there is no obstacle this side. Uh, so whatever observation it will receive or whatever data it will receive. So robot is here, but at some time it goes here. So here it will receive completely different set of experience, different set of data, different set of observations. So its learning will be different based on a different data, rather than if robot had started moving in this direction, it would have received completely different data because environment state, its state would be altogether very different. So here the data it receives depends on the action the agent takes, whereas in these cases we had a fixed set of data irrespective of how the network starts training its weights. It will be trained on those images only. So this is one of the key concepts that you should keep in mind. So now let's look at some of the characteristics. So as I said earlier, there is no supervisor in this learning, but rather it's based on reward signal. So the main aim of the agent would be to maximize its cumulative reward over the time. So this cumulative reward also we call the return. So return is different from reward. So reward the agent received either in some cases after every step or every action it takes, or sometimes the reward is defined to come after a very long period of time. But the return would be the cumulative reward that the agent accumulates over a period of time. And in this case, the feedback is delayed. So it's not immediate. Agent takes an action and it will receive a reward after some time. And as I said earlier, data depends on the agent's action. Like if the robot had started in this direction, it will altogether receive a very different set of data compared to if it had moved in this direction. So the data that the agent receives depends on its actions. Some examples would be a broad set of example of reinforcement learning is while training the machine to play certain games. So like playing a chess. So with initially it will take some wrong moves, then it will get penalized, and for some moves it will be rewarded. And similarly, after playing a number of times, the agent is expected to learn how to play the game of chess and what would be the optimal strategy for maximizing its return. Another example would be making a robot walk. So it will walk, it will tumble, it will fall down, it will learn from its mistake, it will again try to maximize its rewards, and ultimately the robot should be able to walk. And another example is flying a helicopter. Like you have a helicopter and you want it to perform certain maneuvers, like you want the helicopter to make a swing like this, or you want to fly it upside down. So these would be the different maneuvers, and here you can train the helicopter to perform those maneuvers. And let's see how we can define rewards for these examples. So these would be just one way of defining the reward. So first let's understand what a reward is. So reward is a scalar feedback signal. So you should have a scale where you can compare which reward is better. Like if you have reward 1 and reward 2, you would have some mechanism of comparing these rewards, like reward 1 is better than reward 2. And it should be an indicator of how well the agent is doing at time t. So reward will indicate how good the action was. Because the main aim of the agent is to maximize those cumulative rewards over time. And for the chess game, you can define a positive reward for winning the game and negative for losing the game. And in robot walk, we can define positive for forward movement, negative for falling. Similarly for helicopter, if it performs the
trajectory that it was supposed to perform, then it will get positive reward and negative if it somehow crashes the helicopter. So these are some of the ways of defining the reward. Now let's look at a concept called sequential decision making that is very important in reinforcement learning. So the agent selects actions to maximize the total future rewards. So it's kind of sequential decision making. It takes one action and it receives some observation based on that action, and it moves to a new different state, and in the next state it again tries to maximize future rewards from there, and it takes a new action. So it will be a kind of sequential process, and it will have long-term consequences where the agent may lose some short-term rewards in where it finds that it has the potential for a higher reward in future. So the agent will can sacrifice immediate rewards. It's not like a totally greedy algorithm where you have to maximize the reward in the very next step. So some examples would be like some moves in chess may not look very obvious, benefiting in the next step, but in the long run, it may be a good strategy for that move. Similarly, for financial investments, you have to make some investment at the current time, so you take some negative reward at the moment, expecting a higher return in the future. And other example could be that you spend money on getting some higher degree, MS degree, or some higher degree. You spend some money in the current, so you are accepting a negative reward, or you are sacrificing some rewards. You could have saved that money, but you expect that it will give you very high returns in the future, so you take those actions. So those are some examples. Now let's understand this interaction between agent and environment. So at time step t, what agent does? Agent executes an action. So agent executed some action based on its policy, and it receives observation from environment and also a scalar reward. And what environment does? Environment receives actions and emits observation OT plus 1. So in one time step, it environment receives the action, and based on that action in the next time step it will emit an observation and reward. So t we will increment on the environment side. So after we will count it as two step, like agent takes some action at time t, and after at in the next time step environment will emit reward and observations. So you need to keep in mind this interaction, these three things: actions, rewards, and observations, and how agent and environment among interact among themselves. So this was the first part of the introduction. So I will try to give the top view in following videos. So thanks for watching. Give your valuable feedback and don't forget to subscribe if you like my videos. Thank you. Hello friends. This is the second lecture on introduction to reinforcement learning. So in the last lecture we saw how agent and environment interact with each other, where agent performs some action and environments emits some observation and rewards in in response to the action that the agent performed. So we will continue our discussion from there. So the main theme of this lecture would be to describe history and state. So what is history and what is state? So first of all, let's understand what is a history. So as I said in the last video, we have an agent, and anything which is not part of the agent is an environment. So this agent is nothing but the algorithm that we are trying to develop. Like we are creating an algorithm which will learn to play a game of chess. Then this agent will be that algorithm which we will be improving by understanding the state of the environment. So agent performs some action, and in turn it receives some reward from the environment and some observations. So this was explained in the last video. So history is nothing but a sequence of those, like agent performs some action A1, then it received corresponding observation and rewards A2 and corresponding observation and reward, and so on till time t. So history till time t will be the sequence of all those actions, observations and rewards. That is whatever observable variables are up to time t from the agent's point of view, like whatever agent has observed till now and whatever actions it has performed. So whatever happens next depends on the history. So this history is very important because it will be used to determine what will happen next. So the agent or our algorithm, it will select its action based on the history by looking at the history, like what action it performed in the past and what reward it got and what observation it received. So it will, the algorithm will keep on evolving, and its next action will depend on the history. An environment also selects its observations or rewards depending on the history. So now we know what is history, we can try to understand what is a state. So history, we see that it will grow over time, and it will be lots and lots of information. It will be a long stream of information, and it will be very tough to look back at the history, all those data whenever performing a new action, or for from environment point of view giving any new reward. So we pour out useful information from the history, and so the state is the information used to determine what happens next. Instead of history, we will use just the state, which will be information which has been extracted from history. So it can be any function of history. So one example could be that we pick just the previous three observations. It's not very important what happened in the long past. We are more concerned about what happened in the recent past. Like in stock trading also, there are different types of trader, different types of algorithms. Like some algorithms are just for short-term trading, some are for mid to long-term trading. So we have some moving average graphs, like this moving average will be like 20-day moving average, 5-day moving average. So it will take into consideration the closing prices of the stock in the past 20 days. Similarly, 5-day moving average will consider the prices of a stock in the previous 5 days and ignore any old data. So these are very practical examples used today. So one feasible definition of a state was to keep just last three observations or four observations and discard the older history. So so state is a more useful form and more useful information used to determine what will happen next. Now there is a concept of environment state or world state. So environment has some information, and it may not be totally visible to the agent. For example, a robot is trying to perform certain operation. It's trying to learn how to perform certain operations. So it's moving, and based on some obstacle in its way, it will change its action based on the state of the environment. But it sees a very limited view of the environment. It does not fully observe what information the environment has. So there is a complex path, and this is suppose it extends further, and this is the environment, and the robot is somewhere here, and it's walking in this direction. So it observes very limited information from the environment. It does not have information about other parts of the environment. So this state that is maintained by the environment, which it uses to generate next observation of or rewards, is not fully accessible to the environment. Even if it's visible, it may not be very useful for agent for determining its next set of actions. So we have the notion of agent state also. So this state will directly impact our algorithm that is used by our agent. So it will contain the internal representation of the agent or our algorithm. So this is the information used by agent to pick its next action, and it can be any function of history. So we generally denote agent state like this, and environment state by. So in all those concepts, we use Markov assumption concept a lot. So this simplifies our task very much. So any state used by agent, it's a sufficient statistic of the history. So in order to predict the future, you only need the current state of the environment. So state S is Markov if and only if this condition is satisfied. That is here the next state given the current state. So we are in state ST at the moment. So in the given state, if we perform certain action, then what state we will end into. So, so this is state ST, and this is ST plus 1, next state. And we move to this state by performing some action. So given this, we had earlier states like S1, S2, and so on. So we will say that these relationships don't exist. That is, the current state and the current action is sufficient to determine the next step. So these old states don't contribute anything in determining the current state. Only this current state. So the next state given the current state and action is same as the next state given the entire history and the action. So we can say that future is independent of past. So these states were the past. So this future is independent of these given the present. This is the present state. So example, there may be some trading algorithms which are used by high frequency traders. So these high frequency traders trade at a very high frequency. That's why the name is HFT. So like of the order of milliseconds, it can execute multiple orders within milliseconds, and it uses the very near or immediate price fluctuations of the stock market. Like this algorithm may be looking at this is the price of the stock, and there are some technical indicators on top of this like moving averages as I explained earlier, and here is one trigger point. So these all technical indicators will be using a very small horizon. It will not look at the entire price of the stock since uh, past 20 years or 30 years. So for example, it looks at just past 20 days prices. So in this case, one state will represent a price band of 20 days. So we will set this as representing one state. So st minus 1 would be the price 40 days back, price between 40 days back and 20 days back, and st will be price in the previous 20 days. So this indicator will depend on just the price in the previous 20 days. So this would be this we modeled as a Markov based on Markov assumption. So here the definition of state will be the price in the previous 20 days. So with this I will end today's video and I will continue the introduction of reinforcement learning in next a couple of videos. So stay tuned for that, and feel free to give any valuable feedback on how I can improve these videos, and don't forget to subscribe my channel if you like my content. Thank you. Hello friends, this is the third video in the series of lectures on reinforcement learning. So today's main target would be to study the environment, and through that we will come to know about Markov decision process. So we already know that reinforcement learning constitutes of two main players. So one player is agent, which takes actions, and the second player is environment, which emits some observations and rewards. So today our main focus would be to study environment. So it's mainly two types of environments. One is fully observable and second is partially observable. So first see what is a fully observable environment. So an environment where agent directly observes the environment states. So there is nothing hidden inside the environment. So agent can completely see what's going on within the environment, and so it can directly use environment state as its own state. So here in this case, so observation at time t would be the same at state at time t. So because nothing is hidden from the agent, and the agent does not need to construct its own representation of how environment is functioning. It's given that model. Like if we are creating an agent which is trying to learn some game, and we are feeding the exact rules of the game to the agent beforehand. So it's not the job of the agent to figure out what's going on, but we have given out how the environment functions. Everything is clear. So whatever is the observation in time step t, that it can use as its own state. So agent state is same as environment state, and this is the formally definition of Markov decision process. So this is the good case where agent state is same as environment state or the world state, and this formalism is known as Markov decision process, and we will use this a lot throughout our reinforcement learning. Now the other case, partially observable environment. So here the agent indirectly observes the environment partially. It only partially observes the environment. It does not have a clear picture of what's going on in the environment. So one example could be a high frequency trader. So the trader who is trading at very high frequency, it's not an investor, he is a trader, and the algorithm that is being used there looks at only the current prices. So it's not concerned with the historic prices of the stock market. It looks a very small region which is close to the current price, and it only observes that price. It has no data about what was the trend, what is the trend, and how has the stock behaved in different situations. So this trading algorithm has a very narrow view. It observes only a small part of the environment, not the complete environment. Similarly, a robot who is learning to walk, so environment may be a very complex path, but the robot is walking currently here, so it has a camera vision and it observes very limited part of the environment, and it will make decision based on that. It will not know that if it goes 100 meter ahead and then go left, then there will be again a left turn. It has no idea about that. It has to take decision based on whatever it can observe. So it has a very partial observation about the environment. Similarly, a poker playing agent observes only the public cards that is shown and not the card which are to the other players. So in this case, agent state is not the same as environment state, and formally this is the definition of partially observable Markov decision process, or in short POMDP. So since agent cannot use the environment state because it does not have a clear vision of what's going on inside the environment, it has to construct its own representation of the state, of the agent state. So it can construct its representation of the state in various ways. Like one way could be to take the entire history as its state. So whatever value it has observed or whatever rewards it has got till time step t, it will consider that as a state, that is a valid representation of state. And other can be that it takes a probabilistic approach or Bayesian approach, where it assumes uh, what's the state of environment at time t. What's so with probability this p1, the state of environment is s1, and similarly with probability pn. So it does not construct exact representation of state, but it takes a Bayesian approach. That what is the probability that environment state is s1, so p1. So this sum of all p1 to pn, it should be 1. So it creates a Bayesian or probabilistic approach, and it constructs view of environment. It guesses what the environment state currently is. And another way could be that it defines some function which depends on its previous state. So it defined some state in the previous time step, but it received some observation OT which changes its assumption about whatever state it has defined. So it will modify its current state depending on what was the previous state and the new observation. And another example to make it more clear would be like many people play games on the mobile phones. Like if we have a game today, we have a game which is very popular called Temple Run. So here the agent is running, and it faces several obstacles. Like sometimes it may face some fire. In that case, it has to jump over that, and in other case, it may jump into water, and then it may get a rock or something else or a piece of wood in its path. In this case, in case of rock, it would have to jump or take sideways, and in the case of this wood on the top of this water, it has to just slide underneath that. So the agent takes its decision based on what it observes. It has only a very small vision of the environment, and it does not fully observe what's going on. So how environment is deciding what next hurdle to add to the scene. So this is completely hidden from the agent. So this will also be an example of a POMDP, that is partially observable Markov decision process. So that's it. I will end today's video with that, and in next lecture we will focus on this agent parts. So today we saw different types of environment, and in next video we will see what are the components of agent. So we will explore that in the next video. So thanks for watching, and don't forget to subscribe. We will continue our discussion on reinforcement learning introduction. In last video we saw the different types of environment, and we saw that environment can be either fully observable or partial observable. So this we call Markov decision process, and this formed the basis for POMDB, partially observable Markov decision process, where the state of the environment was known to the agent. An agent did not need to construct its own view of the environment. In this video, we will focus mainly on agent and the various components of this agent. So an agent has maximum it can have 3 components, but all of these components are not required, and some of these will be present and some of them will be absent, and we will see in further videos categorization of agents based on the presence or absence of some of these components. So an agent has policy, value function, and model. So let's see what is policy. So policy defines the agent's behavior, like if agent's current state is S, and then what action should it take given the current state. So we will say that policy determines the agent's behavior. So this policy is defined for a given state, and this policy will determine what action should it take. So it's expected that we will define a policy which will help us in taking any action in a given state, and this policy can be either deterministic or stochastic. So deterministic means that this policy will explicitly say that if you are in this state, you have to take this action. So it's give a deterministic answer, whereas stochastic will give different sets of probabilities. It will give what is the probability that you take action A given state is S, whereas this deterministic policy will clearly say the action given a policy. So this A will be determined by policy function, whereas this probability of an action will be determined by this stochastic policy. Now let's look at value function, our second component of the agent. So it's a prediction of future rewards. So if we have defined a policy, then based on that policy, this value function will say that if from state S, what is the expected future reward. Over time. Given that you are in state S at a given time. So let's understand this clearly. So you define a policy and you are in some state, then you need some way of comparing which state would be better. So which state is a good state, which state is a bad state. So this goodness or badness of state is determined by expected future rewards from that state. So if a state S1 is expected to give more future reward, so if you expect that from state S1 you will get more future rewards than the state 2 with the same policy, then you will say that state S1 is better state, because the agent's main objective is to maximize the expected future rewards. So this value function is a prediction of future rewards, and it will help in comparing which state is better. So it's a parameter for determining the goodness or badness of a given state. Now let's look at the third component, which is model. So what is a model? So agent does not have always a clear view of the environment. Like we saw in some examples, a robot is walking somewhere in the room and it has a very limited view of the environment, and it has to make its decision based on that. It has to guess how environment will behave depending on what it has seen so far. So if this robot came this way and went here, and here we have some other paths, and this side also. So agent came through this path and is currently here. So it built some state of the environment like this, and it can see some path ahead. So it has this view of the environment, but the complete environment is this. So this view of environment that is created using the user's the agent's experience and observations, this will be model. So based on this only, the agent will guess how the environment is behaving. The agent tries to build a view of the environment. So model is used to predict what environment will do next. So it's not the actual environment, but a view of the environment, agent's view of the environment, and it will have two components: transition model and rewards model. This transition model, it will determine what is the probability of going from state S prime from state S given an action A. And this reward model will say the expected reward if the current state is S and an action A is taken. So this model have two parts: transition model and rewards model. Now let's look at some examples. So we have a grid, and the agent is currently here. So this is the starting point and this is the ending point or the goal, and some of these are bricks that the agent cannot enter these places. And it's given that every state has some reward. -1, if this is 0 0 0 1, -1, -2, -1, -2, -1, and so on. So what the agent will do, it will, let's say, come here. Its aim is to reach the goal in the minimum possible time. That is, it has to get maximum rewards. So we have -3 here, -2 here, -2, and -1. So if it goes this way, it will have the maximum score. So in the model's point of view, so the agent will just see this part of the environment because it has came this way. So this is a model because it's the agent view of environment. It does not know about the other part of the environment. Now for the same example, we will see what are policy and value functions. So we have seen model. So this will be the model and the corresponding rewards. The agent has no idea about other parts of the environment. And let's see what is the policy. So the policy is if the model agent is here, it goes upwards, here also upwards, here also upwards, this way, and it reaches the goal. In this video, we will see the broad categorizations of RL agents. In our last video, we saw that an RL agent has three components, that is model, value function, and policy, and all of these may not be present in all the RL agents. So we will categorize our RL agents based on the presence or absence of those components. So first is the value based RL agent, second is policy based, third is actor critic, and this is just the first way of categorizing. So let's see these in detail. So what is a value based agent? So in value based agent, we have a value function. So RL agent uses the value function for making its decision of the future, which state it should go to next depending on the value function. And the policy here is implicit. So for example, if you are in a grid similar to what we saw in earlier examples, and some of these states are not reachable, and this is the destination state and this is suppose the starting state, and we define value function for each state, that what's the expected future reward from that state. So if the agent is in this state, then we don't need a policy. We can see that the value function in this state is -5, this side it's -6, and this side it's -7. So this is the best state it can go to. So using value function, the agent decides what action it should take. So it did not require policy. So this kind of RL agents are called value based RL agents. Next kind of RL agents are policy based, which store policy and they don't need value function. For example, if we take similar grid, and we define a policy for each state, like in this state go left, this state go left, this state go left, this go up, 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 and so on for other states. So if RL agent is in this state, knows that the policy says that go up, so it will go up to the next state. So it did not use the value function for making its decision, it used the policies to defined by this RL agent or the algorithm. Next is the actor critic, which stores the value function as well as the policy. So it's kind of takes the advantage of both of these types of agents. Next way of categorization is based on the presence or absence of model. So here we just saw value and policy. Now we see the third component of RL agent, that is model. So the presence of or absence of model also categorizes RL agents. So first is model free RL agent. So in this case, there is policy and or value function. So one or both of these may be present, but there is no model. So the agent does not try to build a model of the environment, that it does not try to understand how the environment is working, but rather it tries to build a policy or value function based on its experience to maximize the future reward. So whatever it has seen so far, based on that it will try to take the further action. It will try to build a policy or define the value function of a state, and it will not try to understand how the environment works. So this type of RL agent we will call model free RL agent, because it does not try to build a model of the environment. Next type of RL agents are model based, which will have policy or value function or both, and they will also have a model. So they will first try to build a model of how the environment works. The first step is to build the model of environment, then figure out the optimal policy or value function. So these were the broad categorizations of RL agents. Thanks for watching, and don't forget to subscribe my channel for my future videos.
Learning and planning are two important concepts in reinforcement learning. So with sequential decision making, there are two fundamental types of problem. One type of problem is reinforcement learning and the second type of problem is planning. So let's see what is the difference between these two. In reinforcement learning problem, the model of environment is unknown to the RL agent. So the RL agent has no idea how the environment functions. RL agent interacts with the environment and tries to understand how the environment functions. So it's kind of a trial and error. And based on that, agent tries to improve its policy so that its future rewards are maximized. In planning problem, model of the environment is known to the agent. So no interaction is required for exploring the environment. Agent plans by performing computations based on the knowledge of environment, based on the knowledge of model of the environment. So it's thinking and planning ahead as compared to trial and error in case of reinforcement learning problem. And based on that, agent tries to improve its policy for getting more reward in the future. So let's take an example of this. So for one example of planning could be that you are told the rules of the game, like you are playing a chess game and you know that what steps are valid and what are invalid. So you are told beforehand. So your task is to plan that what if I move here or what if I move after 2 steps, what will happen. So it's kind of thinking ahead or planning ahead. But on the other hand, an agent may not be told how the chess game functions and it will just try to explore the environment. So it will try to go here and it will get a feedback that it's an invalid move and it will try several other moves and it will get feedback in return that which moves are valid or invalid. So after some time, it will figure out the rules of the environment, how the model of the environment is, and then it will try to maximize its returns. So these are the two fundamental problems in reinforcement learning. Thank you. Exploration and exploitation are the two fundamental concepts in reinforcement learning. So let's see what is exploration and what is exploitation. So exploration means finding out more about the environment, and this may involve giving up some immediate rewards for maximizing future rewards. For example, you know that some action at a given step, if agent is in one given state and if it takes particular action, that action is profitable and it gives some reward. So one possibility would be that the agent keeps on taking that action because it's giving some positive reward. And the other step could be that the agent tries to explore some other action. So agent is in state S1 and it takes action A1 and it gives some positive reward R1. So if it keeps doing that, it will be profitable, but it may not be the best reward that it can gain from this state. So it may be possible that by taking some other action A2, it may gain some reward which is equivalent to 2R1, 2 times R1. So it has not explored this yet. So this thing is called exploration, and continuing on some known action to get some reward is known as exploitation. So exploration is finding out more about the environment, and it may be possible that action is not good and it may give some negative reward. So agent has no idea, but it may give some greater reward also. So here it involves giving up some immediate rewards. But if it finds some other action which is more profitable than A1, then in future, in the long term, this will generate more reward. The other concept is exploitation. So exploitation means to use or exploit the known or profitable information about the environment to maximize immediate rewards. So there should be some trade-off between these two. One agent should not just go on exploring things, and on the other hand, it should also not just keep on taking the same action, because there may be some better action available which will be known only after exploration. So there is a trade-off between exploration and exploitations, and RL agent's objective is to find a policy which will maximize the future return. So it can forfeit some of the immediate rewards, but the future return would be more. So it's important to keep a balance between the exploration and exploitation. Let's see some examples for. So if some advertising is popular and some advertisements are generating good amount of revenue for some company, so exploitation would be showing the same profitable ads repeatedly because it's generating revenue. But exploration would involve showing some new ads which may be more profitable than this earlier ad. So there should be a balance between these two, that how frequently we should show some new ad and try to explore more options. Some other example would be that you have tried some restaurants, you have some favorite restaurants and you like going there and you keep on going there. But there is a possibility that there may be some other restaurant in your neighborhood which is much better than your favorite restaurant. So you may also like to explore sometimes. So the main thing is how you can balance between exploration and exploitation, and that is one of the key concepts in reinforcement learning. So thanks for watching and don't forget to subscribe my channel. Prediction and control is another common problem in reinforcement learning. Prediction is the computation or estimation of consequences of an action. So here the policy is given. So agent is in some state S and under that policy it takes some action A. So prediction will involve evaluation of how good this action is. So policy is given and the goal is to measure how well it performs under the given policy. That is, the goal here is to predict the expected total reward from any given state S, assuming that the policy is defined. So prediction means basically predicting the future. So let's see how it is different from control. So control is basically optimize the future. Prediction was just predict the future. So here policy is not fixed. The task is to find the optimum policy. So given some state S, what is the optimum policy? So the agent if goes here, what is the reward? What if it goes here, what is the reward? So there are a bunch of different actions available, and which action would be most rewarding. Depending on that, the agent will decide what policy it should finalize. So here the goal is to find the optimal policy, whereas in the prediction, the policy was given. So find the policy pi that maximizes the expected total reward from any given state. This ends the basic introduction to reinforcement learning, and from now next video we will dive deep into the reinforcement learning. So thanks for watching and give your valuable feedbacks in the comment section below, and don't forget to subscribe my channel for my future videos.